Hi all and welcome back. In this lesson we're going to be looking at number theory, which is just the study of numbers and their properties. Some numbers that we use are, seen more often than others. One of those is the natural numbers, which are the counting numbers. So when you think of when you start counting, you start at the number one, and then you really don't say any decimals, right? Or fractions. It's just any number you would count with up to infinity. So starting at 1, 2, 3, 4, 5, and so on. Okay. You can take any natural number and express it as the product, which again is the answer to a multiplication problem, of two or more natural numbers. So if I took the number 12, I could write it as 4 times 3. So it's the product of two or more natural numbers. So it's the same thing with the number 17. You can write it as 17 times 1. Okay, natural numbers can have many factors. A factor is an important word. It's just the natural numbers that are multiplied together to give you that product. Another important term that we use is the word divisor and divides and divisible. So what do those all mean? If you've got two numbers that are natural numbers, let's call them A and B. A is a divisor of B, or A divides B, okay, which is symbolized using this vertical bar. That's A divides B. If the quotient of B divided by A has a remainder of 0, so in other words, if I take 8 divides 24, 24 is divisible by 8 because 24 divided by 8 is 3 and the remainder is 0. So as long as there's no remainder, that means that the one number is divisible by the other. Okay, so here 4 divides 12, or 12 is divisible by 4 because 4 goes into 12 and even 3 times. There's no remainder. Okay, on the other hand, if I wrote this, that would be incorrect. That is saying 7 does not divide 12 because 7, you can't divide 7 into 12 perfectly, right? There's a remainder. Two other types of numbers that we see quite often are prime numbers and composite numbers, okay? And every natural number greater than 1 can be classified as prime or composite. 1 is neither prime nor composite. It's classified as what's called a unit, right? So anytime we hear the word unit, we think of 1. A prime number is a natural number greater than 1 that has exactly two factors, 1 and itself. So some prime numbers are 2, 3, 5, 7, 11, and 13 because their only factors are their number times 1. Okay? If you're not a prime number, you're a composite number. Composite numbers are natural numbers that are divisible by numbers other than itself and 1. So for example, 4. 4 is composite because not only can you multiply 1 times 4, you can multiply the factors 2 times 2 to give you 4. Same thing with 12, right? You could do 1 times 12, 2 times 6, 3 times 4. And this is a big typo. This should say 2,000 years ago, the ancient Greeks developed a technique. It was called the sieve of Eratosthenes, who was a Greek mathematician. He determined which numbers are prime and which are composite by using this kind of like pattern that he came up with. So the first thing you do is you cross out the number 1 because 1's neither prime nor composite. It's a unit. You start with number 2 and you circle it. And you cross out all of its multiples. So a multiple of 2 would be 4 because 2 times 2 is 4. 6, 2 times 3 is 6. 8, 2 times 4 is 8. So you're going to cross out all the multiples of 4, right? Which actually just ends up being all the even numbers, or multiples of 2, which are all the even numbers. Okay, and this is just up to 50. Okay, then you circle 3, so the next number. And you cross out all its multiples that haven't been crossed out yet. Okay, so 3 times 2 is 6, 3 times 3 is 9. I need to cross out the 9. 3 times 4 is 12, 12 is already crossed out. 3 times 5, 15 needs to be crossed out. 3 times 6 is 18, 3 times 7, 21. 3 times 8 is 24, 3 times 9 is 27. 3 times 10 is 30, 3 times 11 is 33. 3 times 12 is 36, 3 times 13 is 39. 3 times 14 is 42, 3 times 15 is 45. And then 3 times 16 is 48, and then that's it, right? I'm up to the number 50 already. Then I'm going to do the same thing with 5. Okay, so 5 and its multiples. So 5, 10, 15, 20, 25 is not crossed out. 30, 35, 40, 45, and 50 is already crossed out. Okay, circle the 7, 7, and then 7 times 2 is 14. 7 times 3 is 21. 7 times 4 is 28. 7 times 5 is 35. 7 times 6 is 42. 7 times 7, that's the only one that's not crossed out, that's a multiple of 7, 49. And then we've got 11. Okay, now here's the deal. We stop circling when we get to a number where you square it and it's more than that number there. So like for instance, 7 squared is 49. 49 was less than 50. Okay, so I can keep going. 11 squared is 121. That's more than 50. That means this is the last number I'm circling and I can stop. And every number that is not crossed out that is going to be circled is a prime number. So these should all be the prime numbers that are left over, as you can see. So any number, and it might help if I colored them. Any number that I circled that was not crossed out are your prime numbers up to 50, which means that they only have 2 factors, 1 and themselves. So pretty cool to think that was developed 2,000 years ago. They had a lot of time on their hands. So speaking of divisibility, there are some tests we can use to see if really large numbers are divisible by 2 through 10. Now you might wonder, well, how is this even helpful? Well, if you have to find a greatest common factor or a least common multiple, it actually is very helpful. So there's a chart you can use that will tell you the divisibility rules. Okay, so let's take a look. And if you want to pause and read it, that's fine. A number is divisible by 2 if it's even, so that's easy to tell. If you have a really large number, just look at the last digit. If it's an even number, that makes the whole number even. So it would be divisible by 2. And again, divisible means that that number can divide into that number evenly with no remainder. A number is divisible by 3 if the sum of the digits of the number is divisible by 3. So if you take the number 924 and you add each of the numbers 9 plus 2 plus 4, it gives you 15. 15 is divisible by 3, so that means the number 924 is divisible by 3. A number is divisible by 4 if the last 2 digits of the number are divisible by 4. So if you look at just the 24, 4 can go into 24, right, 6 times. That means 924 is divisible by 4. A number is divisible by 5 if it ends in a 0 or 5. So this number 265 is divisible by 5 because it ends in a 5. But 924 is not divisible by 5 because it ends in a 4. The number 6, a number is divisible by 6 if it's divisible by both 2 and 3. So these two together. So if you think of both of these together, so both 4 divisible by 6, it has to be an even number, and when you add the digits, it should be a number that 3 can go into. So 924, it's even, and if we add the digits, as we saw here, we got 15, 3 can go into 15. So because it's even and because it's divisible by 3, that means 6 can go into it. Okay, so if you think of it as this, two separate things, right? It's got to be even, and the number has to be divisible by 3. The number, to tell whether a number is divisible by 8, if the last 3 digits of the number are divisible by 8. So if we take this number and divide 824 by 8, 8 goes into 8 one time, 8 goes into 24 3 times. So since the last 3 numbers are divisible by 8, the whole number would be divisible by 8. A number is divisible by 9 if the sum of the digits of the number is divisible by 9. So it's very similar to 3, okay, except we add the digits and make sure it equals 9. So 837, if I add 8 plus 3 plus 7, I get 18, and 18 is divisible by 9. So 837 is divisible by 9. And then a number is divisible by 10 as long as it ends in a 0. There was no divisibility rule for 7. It's a little strange, but basically what you do is you take a number, like let's say 203, you remove the units digit. So remember, the units digit is the number, the digit to the very far right. So the 3, you remove it and you double it. If I double 3, I get 6. And then what you do is you subtract the leftover digits, 20 minus 6, which is 14. Since 14 is divisible by 7, then that means 203 is divisible by 7. So it's a little different than the other rules. It's a little bit more involved. So what we would want to do for this is take this large number, and I want to know, is it divisible by all of these numbers here? Okay, so it's a yes or no, and why or why not? So is 563,244 divisible by 2? If you want to pause and try to answer these and then unpause when you're ready, that's fine. The answer is yes, it is divisible by 2, and the reason is because it's even. So because it's an even number, yes, it is divisible by 2. To tell if a number is divisible by 3, remember you want to add the digits. And if I add those digits, 5 plus 6 is 11, plus 3 is 14, plus 2 is 16, plus 8 is 24. So this should give me 24. Is 24 divisible by 3? So in other words, can 3 divide into 24 evenly? Yep, a perfect 8 times. So that means yes, it is also divisible by 3. In letter C, we want to know if this number is divisible by 4. So remember, to tell if a number is divisible by 4, you look at the last 2 digits. And since 4 can divide into 44, or 44 is divisible by 4, goes in 11 times evenly, then yes, it is divisible by 4. 5 and 10 are the easiest. So for 5, it has to end in a 5 or a 0, and it doesn't. So it does not end in a 5 or 0, so that's a no. And if I skip to H, it would have to end in a 0 for it to be divisible by 10, which it does not. So therefore, that's a no also. In letter E, remember it's a combination of A and B. So if you want to tell if a number is divisible by 6, it has to be even, which it is, and it has to be divisible by 3, which it is. It was a yes for both of those, so it's a yes for letter E. Is it divisible by 8? So you want to look at the last 3 digits now, so 244, and can 8 divide into 244 perfectly? If you're not sure, you can try 244 divided by 8, and you get 30.5, so it does not divide evenly. It's 244 is not divisible by 8, so therefore, I'm going to put a little slash through there. No, that number is not divisible by 8. And then 9 is very similar to the rule for divisibility by 3. If you add the digits, and if it's divisible by 9, then it would be divisible, that whole number would be divisible by 9. When we added the digits, we got 24. And 9 cannot go into 24. So that's a no. Okay, here's some practice problems for you. What you're doing is you're deciding whether it's a true or false statement. And if it's false, you want to modify it to make it true. Okay, so try those. If you have questions, again, always feel free to ask. We're next going to look at something called prime factorization of a number. So we looked at the word prime before. Remember, a prime number is just a number that has factors of 1 and itself, and that's it. And this prime factorization is just a process of breaking down a composite number into the product of prime numbers. So for example, the number 24, I can break that down into all prime factors. 2 times 2 times 2 times 3 gives me 24, and 2 and 3 are prime numbers. We can abbreviate that, and instead of writing 2 times 2 times 2, we can put 2 to the third. So that power represents how many times we're multiplying the base 2 by, and then times 3, okay? The fundamental theorem of arithmetic states that every composite number can be expressed as a unique product of prime numbers. Unique means different, right? So you can take any composite number and write it as a different product of prime numbers. And there's two methods that we can use to determine prime factorization. That's called branching, which is a factor tree. So these are the branches. And then division, which is here. So if we wanted to write 1500 as the product of primes, for example, okay, 1500 is a big number. The nice thing about a factor tree or branching is you can pick any two numbers that multiply to give you 1500. So 15 times 100 works. You could have used 150 times 10. And the whole goal is to break those composite numbers into primes. So 15 breaks into 3 and 5, right? Those are prime numbers. 100 breaks into 10 times 10, which you can break down into 2 times 5 for each. And that's it. You're done because those are all prime numbers. You can rewrite this now as 2 squared because there's 2 2's, times 3, there's only 1 3, and then 5 squared. And remember, you're multiplying all of these numbers together. So it doesn't matter what order you write your answer in. I usually put them numerical as well. And you can see here, here's another factor tree using different numbers. You still end up with the same answer. The division method, what you do is you divide the number you start with by the smallest prime number that will go into it that's divisible. So 2 goes into 1500, right? Because it's even. And 1500 divided by 2 is 750. Okay, I can divide 2 into 750. That would give me 375. Now, because it ends in a 5, it's odd. I know 2 will not divide into it. But if I add the digits, 3 plus 7 plus 5, 3 plus 7 is 10, plus 5 is 15. I know 3 can go into 15, so it goes into 375. 3 goes into 75 125 times. Okay, 1 plus 2 plus 5 gives me 8. 3 can't go into 8, so I have to try the next prime number bigger than 3, which would be 5. 5 goes into 125, and I know that because it ends in a 5. 125 divided by 5 is 25. And then it ends in a 5 again, so I can divide by 5 again. 25 divided by 5 is 5. And then to get your answer, it's 2 squared times 3 times 5 to the third. There's those 3 5s there. So we're going to practice using both methods for these problems here. I'll do one of them with you, and then you all can try one of the other ones on your own. So let's take 180, for instance. For 180, I want to first break this down into two numbers that multiply to give me 180. So I know since it ends in a 0, 10 will go into it. It's divisible by 10, so I could do 18 times 10. 18 and 10 can be broken down more. So 18 can be broken down into 9 times 2, and 10 can be broken down into 2 times 5. 9 is not prime yet, but 2 and 5 are. So 9 I would break into 3 times 3. And then I'm just going to carry these other numbers down because they're all prime, I'm finished. I'm just going to write it in order. So I've got 2 2's, that would be 2 squared. I've got 2 3's, that would be 3 squared, and then 5. And if you multiply them, and you could check it on your calculator, 2 squared times 3 squared times 5 gives me 180. So that's using the branching method. The division method, I'm going to start with 180, and you divide by the smallest prime number that will go into 180. So 180 is even, so 2 will go into 180. Okay, 180 divided by 2 is 90. 2 goes into 90. 90 divided by 2 is 45. Now I know 2 will not go into 45, but 3 goes into it. 3 goes into 45 15 times. Okay, 3 goes into 15 5 times. And then that's it. So let me draw my line here. So my answer is going to be 2 squared times 3 squared times 5. Okay, you all can try 315. Another important concept is this greatest common divisor, right? Which is the largest natural number that divides without remainder every number in that set. Okay, so what's the largest number that will go into 36 and 90, for example? So there's a couple ways you could do this. One way is you can list out the divisors of 36. Okay, so what numbers will divide into 36? Well, I know 1 times 36, 2 will go into it, 3 will go into it, 4 will go into it, 6 will go into it, 4 times 9, 3 times 12, 2 times 18, and 1 times 36. And then you're going to have a longer list now of the divisors of 90. So what numbers will divide into 90? 1, 2, 3, 4 does not, 5 does, 6 does, 9 times 10, 6 times 15, 5 times 18 will work, 3 times 30, 2 times 45, and 1 times 90. And I don't think I missed any. Now we got to look and see what's the greatest of the divisors that they have in common. So if I go through this, it looks like 18 would be the greatest one in common. So my greatest common divisor, also known as AKA, the greatest common factor, right? GCF, it's the same thing.
Hi all, in this next part of the video, we're going to look at polynomial functions and we're going to find the zeros and state the multiplicity and determine if the graph will cross or touch at each zero, and then also look at the end behavior.
Now, there's another way.
So in this first problem here, we have this polynomial.
Let's say we have numbers that are really
I
big,
want
like
to find the
315 and
zeros, which
450.
remember
I mean,
just
you all saw
the x-intercepts.
writing the
So I'm going to
factors
take
out for
my
36 and
expression
90. There
and
were a lot, and
just
if you
set
miss
it equal to
you
0.
could miss the greatest common factor. So another way you could do it is make a factor tree or branching.
And remember that we're going to apply the zero
So
product
I'm gonna
property,
do
which just means take each of the
factor tree for
factors and set it
315.
equal to
So
0.
two numbers
I
that
don't have to worry
multiply
about setting
to give me
1/10 equal to
315,
0 because it doesn't,
which,
right? So we're just going to take
it could be
x
any
minus
numbers,
2
like,
to the third
I know
and make it equal 0.
times something will give me
2x minus 1 equals
but
0.
also 15 times 21
and x plus
I
2
know will
squared
give me
equals 0.
315.
And
So
my
I can break
exponents
15
tell me
down
my
into 5 times
multiplicity.
3,
So here
and
we know we're going to have a
17 can break- or
repeated root
21
of
can break down
3.
into
It's
3
going to be a
times
multiplicity
7.
of 3.
So now
that just means
they're all
that
prime numbers.
when you
It would
solve
be
this
3
and set it
squared
equal to
times
0,
5 times 7.
it has
I'm gonna do the
3
same
answers
thing
that are
for
the same.
450.
So if you
I know
solve for x here,
45
you're going to get
times
2.
10, right? It ends in
But
a
because
0,
of the
so it's
3, there's
divisible
really
by
3
10.
2's. So
45
x
breaks
equals
down
2
into 9 times
has
5,
a
and 10
multiplicity
breaks down into 5
of
times 2.
2. of 3.
I don't have all primes yet. 9's composite.
And then
So I have
2x
to break
minus
that down
1,
into
if I
primes,
solve
3
that for
times
x,
3.
I get
And then
1
I'm just gonna
half,
carry these other
and that
numbers down,
multiplicity
and
is
then I'm
just
done
1.
because I have all my primes.
And then
So
x
if
plus
I put them
2,
in
if I
order,
set
it's
that
gonna be
equal to
2
0 and solve for
times
x,
3
I get
squared
negative
times
2,
5
and that
squared.
multiplicity
Okay, so now,
is
what I want to do
2.
to figure out what the
Okay,
greatest
and again,
common
the
factor
multiplicity
is,
comes from
you're going to
the
list
exponent.
each prime factor with the
Okay,
smallest
so now
exponent
the multiplicity
that appears
also
in
tells me
each
whether
of
the
those
graph will cross or
factorizations.
touch
Okay, it
the
has to appear
x-axis
in
at that
each.
point.
So first,
So
let's figure
remember,
out
if the
which ones
multiplicity
appear in
is
each.
odd,
So I
it's
see
going
a
to
3
cross the
here and
x-axis
a
at that
3
point.
here,
So
and I see a
the two
5
odd
and a 5.
multiplicities
I'm not going
would
to use the
be
7 and 2 because they don't appear in each one.
this here, because
what
it's
we do
3,
is
3
we
is
list
odd,
out and pick out
this
the
here
smallest
because
one.
it's
So
got
the
a
ones with the
multiplicity of
smallest
1 is
exponent.
odd.
So you have a
it's going
3
to
squared and a
cross the
3 squared,
x-axis
so
there.
they're the
So
same
here it's going to
exponent. So you're just
cross
going to pull that 3
at
squared
x equals
out.
2,
And then you have
and
a
here it's
5
going to
to the
cross
first power and a
at
5
x
squared.
equals
The
1
smaller
half.
one
And you'll
would
see
be
that
5
in the
to
graph.
first.
And then
So I'm going to multiply those together. 3
even
squared, 3
multiplicity
times 3
means
is
that the
9,
graph is just going
and
to
9 times
touch
5
the
is
x-axis
45.
at that point.
So 45
So it's
would
going
actually
to
be the
touch
greatest common divisor.
the graph
That's
at x
the
equals
greatest
negative
number
2.
in common
So
to
you're going to
both
see here,
350
if I pull
and
up the graph,
450. It will divide evenly into both of them.
you can see here how it's crossing at
The
1
last thing we're
half
going
and
to
a
talk
2
about
because
is the
those
least
both
common
had an
multiple,
odd multiplicity.
Okay? So for
And
this
it's
example,
touching
I'm
the
going
x-axis
to
at x equals
make
negative
I'm
2.
going to show
So
you
it's
both
kind of
ways.
hitting
So you could
the
list
negative
out
2,
the multiples,
and then it's bouncing off.
all right, which
And
in
this
this
is going to be
case are
useful when
just,
you're graphing polynomial
like 12
functions.
times 1 is
Okay,
12.
in addition
12
to
times 2 is 24.
finding the
12
end
times
behavior.
3
So that's
is
the next thing I
36.
need to do. So
18
I
times
found
1 is 18. 18
the
times 2 is
answer,
36, and so
my
on.
zeros were
So if
2,
you list
1
out
half,
first the
and
multiples
negative 2,
of
and then
12,
it crosses and touches at certain points. And then letter C is the end behavior. So for end behavior, remember I need to know 2 things. I need to know the leading coefficient.
Okay, I
if
think that's
it's
enough. And then multiples
positive or negative
of
and the degree,
18.
if it's even or
So
odd.
18 times
so
1,
my leading
18
coefficient
times 2,
here, right?
18
I would
times
have
3,
a 1/10 x
18
and then a
times
2x
4,
and an x. So if you
18
multiply
times
them,
5.
you would get 2/10,
Okay,
and then it would be
I'm gonna
x
stop
to the
there because I
6th
already
power
see the common
because
one.
you
So
have an x
this
cubed,
time we want the lowest
an x to the
common
first,
one.
and an x
And
squared.
the lowest one
So if I
that
add those,
see in
I
common
get
here
x to the
is
6th. So
36.
my degree is 6, which is even, and my lead coefficient
Another way
here,
you can
it's
do it is just
positive,
like we
right?
did
We
above
said
with the
positive
branching.
2/10.
Okay, except this time,
So
to
when
figure
it
out the
is
least
positive
common,
and
what you need to
even,
do
remember
is you're
that
gonna
it's
list
going
each
to
factor
point
with the
upwards
greatest
on
exponent,
both
and it
sides.
has
So think
to
of
appear in
x squared,
any of
right?
the
It's positive and even, and it's a
factorizations.
parabola
let's look
that's
at that.
concave up, so
So
it's pointing
if I
up.
make a factor tree for 12,
So when I write my
right, I
end
could do
behavior, I'm going to
maybe
express
4
it like
times
this.
3.
I'm going to talk about the limit
4 breaks down into
as
2
x
times
approaches
2,
positive
and
infinity
then I'm just going to carry
of
that 3
f of
down.
x. So that just means on
So
the
they're all
x-axis,
primes,
so if
so
we
I
look
can
at the
stop
graph,
there. That would be 2
if
squared
we were to
times
go
3.
towards positive infinity on the
And then for
x-axis,
18, I'm going
what
to do 9
is
times 2.
the graph doing on that end? Well, on the
And
right
we know
side,
that
it's
9
pointing
breaks
up.
down into 3
So
times
f of
3.
x is always
I'm
going to
just gonna
approach
bring that 2
positive
down,
infinity.
so this would be 2 times 3 squared.
So this is going to equal positive infinity.
And we can,
And the
for this,
limit
we're
as
going
x
to,
approaches negative infinity
list the factors
just
with the
means
greatest
as you are
exponent
walking
that
along the
appears in
x-axis towards
any of
negative
the
infinity,
factorizations.
again, if you look at the graph, what's
So,
happening to the graph?
First, let's
it's
make sure they
always
appear in any. I
increasing
got a
towards
2
positive
and
infinity
a 2, a
forever.
3, and a 3
So
squared. And
the
if there was
limit
another
here is
number
gonna
here,
also
I would
equal
include it,
positive
right?
infinity.
It's different than greatest common divisor, where it has
Anytime
to appear
you
in
have,
both.
you're talking about end
Here,
behavior,
it's just
and it's
any of the
positive and
factors that
even,
appear.
or
And this time
negative
you
and
pick out the
even. You're going to get the
greatest,
same answer for both
exponents.
limits.
So
okay? Because remember,
if you
both sides
compare
are going to be
2
going in
and
the
2 to the
same
first,
direction.
we would pick out
It's
2
when you
squared.
have odd
And if you pick out
powers that
3
it's going to
and
go
3
opposite.
squared,
So
compare
you'll
them,
get
3
two opposite
squared
answers.
has the higher
One
exponent.
will be positive
So
infinity,
2
the
squared
other
is
will be
4,
negative
3
infinity.
squared is 9, and so you get 36.
Okay, let's try one more. So here we
same
have
answer
f
that
of
we
x
got,
equals x
by
cubed minus
listing
x
out
squared
the
minus
multiples.
2x. So the first
So
thing
you
I
can
need to do is
try,
find the
1 and
zeros.
2,
So I'm just going to set this equal to to
If you have
0.
any questions, please reach out to me.
And
Hope you
this
all
is not
enjoy
factored
the rest
for me
of your
like
day.
letter A was, so I'm going to go ahead and factor it. And here we can factor out an x, and you're left with x squared minus x minus 2. And then I can also factor the inside here. So two numbers that multiply to give you -2 that add to -1, and we get x minus 2 times x plus 1. Okay, and I'm going to set each of these factors equal to 0. And here, as you can see, we don't have any powers other than 1. So for each of those, it has a multiplicity of 1. 1 is odd, so that means it's going to cross. So it's going to cross at x equals 1, it's going to cross at x equals 2, and it's going to cross at x equals -1. So here are your zeros, and it's going to cross in each place. So if we were to actually graph that, you'll see, so if I plug in here, I have my x cubed minus x squared minus 2x. You can see at each of those zeros or x-intercepts, the graph goes right through and crosses. Also take a look at the end behavior. It is going in opposite directions, right? And that makes sense because our degree is a 3, it's odd. So when we're looking at end behavior, my lead coefficient here would be 1, so that's +1. And my degree is 3, which is odd. So remember, positive and odd, the right side's going to go up, the left side's going to go down. They're going to go in opposite directions. So here, if you go to the right on the graph, as x approaches positive infinity, f of x is also going to approach positive infinity. It's going to point up. And as x approaches negative infinity, as you go left on the graph, that's negative infinity. Let me make that more clear. F of x is going to approach negative infinity. So they're opposite for that one. Okay, and you all can try the next problem on your own if you take a look at those examples from above. And in this last problem here, we have a function, okay? And again, you can try this on your own, looking at the examples from above. So you want to talk about how many turning points does this have? You want to find the y-intercept algebraically. We talked about all of that in the last chapter and before. Find the zeros or the x-intercepts and their multiplicity, and then discuss the end behavior as well. Okay, and the only other thing I want to point out to you are what power functions are. There are functions of degree n, and they're in monomial form. So mono means 1, right? It's one polynomial. Okay, it's going to resemble something like this. So if you had like x squared, that's called a power function. Negative 5x cubed, 1/2 x to the 6th. Okay, and what's important to remember is that polynomials resemble a power function when you have large values of the absolute value of x, specifically with end behavior. So x squared, I know it's positive and even, so the graph, remember, is going to go up on both sides. So if I was to take x squared, a power function, and let's say add on to it, like something like this, if you graph that equation, it's going to resemble the power function. So even though it will look slightly different, it'll go through the x-axis in different places, it's going to contain the same end behavior. It's going to approach positive infinity as x approaches positive or negative infinity. Okay, just like this one is negative lead coefficient and it's odd. So remember, negative and odd, it's going to point up to the left and down to the right. Okay, so even if I created another equation using that power function, like something like this, it's going to contain the same end behavior. Okay, that's it for this lesson. Please feel free if you need to go back and review to do that. If you have any questions, please reach out to me.